Hi everyone, my name's Alice Price, and this is the problem that I chose for our Module 2 video presentation. The subject that I have chosen is multivariable calculus, and the reason that I chose this subject is I usually either teach AP Calculus or multivariable calculus. During the fall, I'm teaching a couple sections of both. So AP Calculus has so many fantastic problems already built in from the College Board. But my multivariable calculus, even though the math is high level, most of my problems, honestly, are really more like exercises. So that is where I need the most improvement. So that is the subject that I chose. So the topic that I chose to work on today was just relative extrema and the second derivative test. Honestly, I could have picked any topic in the course because every single topic that we teach really does need a bit of improvement. So I just kind of skimmed through and found one that jumped out at me. So today we're going to focus on relative extrema and the second partials test for locating extrema and saddle points. So I decided to start by just showing what a typical problem would look like. This is really more of an exercise. So find the local maxes, mins, and saddle points for a function, just some random multivariable function. You find your, oops, let me change to pen here. There. So you find your first partials, set them equal to 0. You get usually a little kind of system of equations. It's usually pretty simple. Sometimes it's a little harder, but they're always solvable. And then you solve the system. You find your critical points, and then you apply the second partials test. So you need to find your second partial derivatives, and then your second partials test is doing the product of the second partial with respect to x and x, the second partial with respect to y and y, and then multiplying those together and then subtracting the mixed partial squared. And then if that is negative, you have a saddle point. If it's positive, then you look at your partial with respect to x and x or y and y, it doesn't matter. And if that's positive, you have a min, and if it's negative, you have a max. Now, some of this has to do with concavity, but it gets a little tricky to explain why this works, especially with the mixed partial part. Gets a little complicated with explaining why the second partials test works. When I teach it, we talk about it a little bit, but we don't get too in depth because it is it's pretty complicated. However, applying it can be pretty simple, and I wanted to put kind of a twist on it. So here is my new rewritten problem based on that original one. So I wrote, instead of just giving them a function and saying find the maxes and mins, I said, does a function exist with one saddle point only and no relative or local extrema? If so, show what it would look like graphically and find an equation for it. If not, show or explain why such a function does not exist. So what I love about this problem is, first of all, you're not just handed an equation and then applying what you've learned. You're having to kind of figure things out and make some deductions, and there are so many different approaches that you can take. So I wasn't sure how to show this in the video, so I decided to walk through Polya's steps and then kind of intertwine Schoenfeld's steps in with it. So for Polya's step 1, understanding the problem, I would anticipate that students would read this quietly. I usually try to have at least 30 seconds to a minute of quiet reading where students just kind of read, digest, and think for a minute, then discuss in their groups exactly what the problem is asking. Maybe during the understanding the problem time, they would even start making a conjecture of whether or not the function does exist. Step 2, when they're making a plan. So this is where Schoenfeld and Polya kind of come together. So when they're making a plan, there are so many different approaches, and it's funny that Polya, so many of these approaches, just straightforward old math approaches, work really well for this problem. So you could sketch a picture, you could work backwards. They just learned the second partials test, and so they could try to do second partials test backwards to see if they can back themselves into an equation. They could look for patterns, maybe apply some prior knowledge of what equations look like that have a saddle point. They could do a guess and check. And in this case, if they did a guess and check, I would think they would do it by just using graphing software and just plugging in equations and see what works. And then, of course, students always come up with other methods that I have not thought of. So that's one of the beautiful things about this class is most of the students in there are way smarter than I am, and they can think of things that I would never have, that just wouldn't have occurred to me. All right, so when we get to step 3, which is actually solving the problem, so I kind of outlined some of the different approaches, and this is where I was really thinking more about Schoenfeld's control. I'd been having a little bit of trouble really kind of nailing down in my own mind what control meant. But then I started thinking about the decision-making process in this problem, and it really does make a difference which path you decide to go down. And so what I think might happen for most students is because they just learned the second partials test, most of them, and so I listed this also as a resource, so most of them would think, well, we've just been doing second partials tests, so we're just going to dive in and start working second partials tests and see if we can figure out what works. So this is not the most efficient way to solve the problem. It will work. And one of the things that's fun about it is it might push students to kind of have to do a little bit of integration if they can come up with maybe some second partials and then have to go backwards into first partials and have to go backwards again into an original function. We have not done any integration up to this point. And so having to do integration based on a multivariable function, I think would be a really, really great process for them and would be a really nice, what I put a really wonderful lead into our next unit. However, it would take a while, but I think they could do it if they put their minds to it. Another thing that I thought would be good would be if they started with a picture, then they would get this belief. And the belief, belief I think covers a lot of different things, including your own personal self-confidence. Well, if you start with a picture, and it's hard, sometimes it could be hard to think of a function with one and only one saddle point and no relative extrema. Cross-sectionally, we're kind of used to, they would have been used to seeing functions where like here's the saddle point, but then it goes kind of still has a max or a min or something like that. Whereas in a problem with, or a function with just a saddle point, they'd have to be able to visualize something that goes up forever kind of to the left and right and down forever kind of forwards and backwards, and then you get this kind of saddle point there. It's a terrible drawing, and drawing in 3D again is kind of tricky, and I'm not that great at it. But they could wrestle with that a little bit and figure that out. If they can come up with an image, then they would know it has a solution, right? So as soon as they come up with an image, then they know that they're at least what they're working for, and they can maybe get a little bit of inspiration from there. Resources. So the other thing besides second partials tests that they've learned in their little, what I kind of think of as their bag of resources, resources to me in this class mostly makes me think of prior knowledge. But it might also think of other resources at hand, such as software. But for me, there is a shape that they learned back in a previous unit. It would have been 2 units prior, and so they probably would have long forgotten about it. But there's a shape called a hyperbolic paraboloid, and they learned that name and the corresponding equation 2 units prior. We didn't spend a lot of time on it, but if they can remember that and apply that, they could be done with the problem in a minute. Another thing that they could try is level curves. So they could kind of sketch and see if they could think about, like, what does a function look like with a level curve where it has a saddle point, and maybe see if they could kind of like draw some lines to kind of figure out what would happen if they were doing it with a level curve. So that could be tricky, but it's not a bad path to take. And then let's see. Oh, and then the last thing I thought of, so for guess and check, if they open up a graphing software and just start typing in equations, random two variable equations, trying to find one that has a saddle point and no max and mins, I think that exercise alone could really help just kind of open up some doors as far as understanding how the equations relate to the graphs in a multivariable situation. So the next phase would be looking back, and under Schoenfeld, I know that part of Schoenfeld's goal is to really take the problems and not just think of them as a problem for solving, but also think of them as a problem designed. That was my phone. As a problem designed to lead them to really have kind of a deeper understanding of some mathematical concept. And I think this problem would lead them to a deeper understanding of actually quite a few different mathematical concepts. It might open up some worlds that the students might not have thought of before, because there are so many different directions and approaches that they can take. And during the looking back time, that's when I think a lot of this is going to come out, is when the students actually start explaining how their group approached the problem, and then start listening to how other groups approached it, and having a discussion of what worked well, what didn't work well, what might have been more efficient. Even if it was a less efficient approach, what were the benefits to that approach? So all of this to me would be part of Schoenfeld's kind of like his mathematical generalizations that could be obtained from solving the problem. Okay, so I also mentioned that the fastest method was just looking back or thinking back to a prior unit and remembering the equation of a hyperbolic paraboloid. I don't think any group will think of this. And when I was thinking about this problem, I was thinking about the day that we teach quadric surfaces, and we only spend a day on them. We don't spend any time graphing them by hand because they're so tricky to graph by hand. And I kind of skim through them. I don't emphasize them very much because I know that we're going to talk about them in further detail when we get to our volume chapter. So I kind of skim over it and move on. But I thought that this would be a great way to tie that back in, because if they can kind of have that in their bag of resources before the next unit, we'd be on a much more solid ground walking into our next chapter. So I actually thought about this, and I thought, you know what, I'm going to do an add-on question after we're done with this problem, and kind of tie these the quadric surface equations in a little bit more fully. So then a couple other things I mentioned, level curves. I think my students often just kind of dismiss level curves as like more of a gimmick. And so I think if we sketched the level curve for each student's equation and kind of talked about what does it look like around a max, a min, or a saddle point, it might help us understand level curves a little better. And then especially even the guess and check graphing software, if a student could figure out that if they're just graphing something like z equals xy and they get a saddle point from it, that might lead students in when they see an equation like x squared plus 4xy. Does it have a saddle point? Does it not have a saddle point? If they've gone through this guess and check process, they might have a better understanding of the answer to that question. Okay. So here I'm just mentioning, I've already mentioned the generalizations, but I also wanted to mention that I did come up with an add-on problem once this problem has been completed. I thought, you know what, if we kept going with this, could we go back and relate all of our extrema problems to quadric surfaces? So could the students figure out, does, what what kind of extreme and saddle points does a paraboloid or a hyperboloid or a cylinder or any of those shapes, do any of those have any of these, which ones apply, and then maybe do a quick sketch and maybe sketch a level curve for each of these as well to help tie it all together. Because the more students, I think, make the connections across units, across topics, across courses, I think the deeper that their mathematical understanding will go. And so anyway, I hope you enjoyed this problem, and I hope you have a great day. Thank you so much.